Okay, so hello everyone. My name is Paul Lamar. I am the technical account manager for that I work with Darigold on behalf of the Department of Energy for the Better Plants program. And Darigold was fortunate enough to submit an application for an implant training, and they were awarded that that event. That's going to happen in March, later in March this month, on the 24th through the 26th. At the Sunnyside facility, and it's going to focus on compressed air. In just a minute, we have our expert, Frank Moskowitz, is going to go through some background information on the implant, as well as some best practices and use of the AIRMaster tool. Just a bit of background on Frank. We're very fortunate to have him. He's extremely qualified in this area and comes highly recommended. He's got over 30 years experience in plant engineering. He's got a degree in mechanical engineering as well as training in refrigeration, electrical, and plumbing trades. And for the last 25 years, he's been an associate of DRAW, professional services primarily in auditing, consulting, training, and system design. And his specialty is really in compressed air and vacuum systems. And he is an instructor for the Compressed Air Challenge, as well as an AIRMaster Plus instructor and a DOE expert on compressed air systems. So with that, I'd like to go ahead and turn it over to Frank, and he can get us started here. Frank?
Okay, thanks a lot, Paul. So you guys have it, and if anyone has any questions, I guess you would just chat it in, and if it's important enough, either Vestal or Paul just, maybe interrupt me, let me know. Other than that, I guess we'll just wait till the end for the Q&A. So let's get started here. I have slides that are going to go over various aspects of this implant. Basically, we start off with what is an implant training, and I can read it. You could read it. It's system-specific workshops, and there's, as Paul mentioned, there's various experts. We train, we help you identify, and the main thing is to implement anything to do with energy-saving projects. So there's partners host an on-site 3-day. Sometimes it was 4. Some companies actually went to a 4th day, but this is a 3-day. And you invite others to attend. And from the attendee list, I know there's a lot of folks from other cities other than the Sunnyside plant. So that's coming in. The mention of workshops that have other energy uses. It could be compressed air, it could be fans, motor-driven systems, steam, process heating, pumps. So Darigold chose compressed air, which I'm glad they did because it brings me here, and I think compressed air has the most opportunity for energy savings in any plant. So this is a good move forward. The expertise it helps companies overcome common barriers. Right? So what's a common barrier? Basically, it's lack of technical expertise in the plant right now, and it's insufficient senior management time. There we go. Okay. So what's important on this paragraph that's up here, and it's not a hit on management that they don't really want to implement, is that no one has the expertise. No one has the expertise to figure this out. And that's why we do this. We give you the expertise to figure it out. Let me just wait a second while we try to find the source of that noise.
And we saw that data, and you don't always have
everybody.
Yeah, Frank, I'm working on this at the moment.
Okay.
So can I just say, if anyone is on the line listening in, can they mute their phone so that the background noise is minimal? Thank you.
Hey, Frank.
Yeah.
This is Vestal. I made you the host. For some reason, I was unable to I should have muted everyone before I passed the controls to you, but if you could just pick any user at random and right-click, you can mute everyone, and then you can unclick for yourself to unmute you.
Able to do something.
Beth, did you hear me a second ago?
No.
We did not.
All right, well, it doesn't give me an option to unmute me personally. It looks like it muted everyone, and when I click on my name, only unmute all is available.
Right now, you sound pretty good.
All right, let's go for it again.
Yeah, thank you, Frank.
No problem, no problem. Okay, so as I was mentioning, the problems that most folks have, it's the lack of expertise, and it says here, insufficient senior management buy-in, and that kind of sounds like a dig. It's not. It's just that senior management is pretty busy, if you know that. And the energy saving opportunities, there's not enough expertise in most plants to explain why they should move forward, why the return on investment is so amazing, and how it's actually profitable. So we do take a look at the entire facility and the compressor end in this case, and other folks from other facilities get to share it, and they get to understand what's going on in this plant. They take it back and they can replicate it in their own plants, and it just works out really well. Every plant we've done is just amazing. As a matter of fact, this goes back to 2011. DOE has conducted 40 in-plants, 765 participants, close to 2.7, I mean, this is a huge number, trillion BTUs in annual energy savings and more than 14 million in associated. So this program is a success. And compressed air, like I mentioned, is one of the easiest. We'll skip this introduction on me since we already had Paul give such a nice introduction there. Overview, compressed air system energy savings. Basically what we're going to do is figure out how to plan for this assessment. And this webinar is going to prepare us for that. We'll talk about baseline measurements. We'll talk about compressed air energy opportunities, a little bit on the software tool. We have Log Tool, and we have AIRMaster. And then at the end of this presentation, we'll talk about the agenda that will take place during the 2 or 3 days that we're on site. It's not much time to get things done, so we got to have an agenda and pretty much try to stick with it. So this slide here, very important from Compressed Air Challenge. What it basically tells us is, if you look at the pie diagram, it has electricity, it has a piece of the pie as a slice for equipment, and it has a piece of the pie as a slice for maintenance. And what you can see from it is that the electricity cost is literally 10 times more than the equipment price. Now, I used to sell air compressors a long time ago. I used to sell pumps. And that's the part that's really tough. If you're in sales, you get beat up pretty badly on the price. You could talk about energy savings until you're blue in the face. No one cares about it. It's all about the price of the equipment. Yet it really is nothing compared to the total package and year after year what you're spending. So this is a pretty important component here. And we're looking at the waste. And the waste is going to be, with compressed air, the most amazing thing you've seen. Because with a compressor, like as if you were buying a light bulb, most of the energy that you pay for goes off as heat. Now this is a pretty cool arrow because it's got a whole bunch of things happening. I got two components here. I've got the bottom portion, which is blue, and then it has the red going off as heat, and this little bottom slick piece down here. 15%. So the electricity consumed by the compressor to generate compressed air, and this is typically the 100 PSI systems. This means whatever dollars you spend on compressing air, 85% of it went off as heat. It's like I mentioned the light bulb. You know, why is the incandescent light bulb getting so beat up these days? Because when you turn on a light bulb, 90% of it is heat, and only 10% of it is electricity, or is light rather. So a compressor is actually way better at making heat than it is at making compressed air. But you don't buy it to make heat, we buy it to make air. So that's one of the major inefficiencies. It's thermodynamics, and during this little seminar, we're not changing thermodynamics. But take a look at the green. This is the air delivered into the pipe by the compressed air system, and it doesn't show it all going to the end. It shows production gets a piece, it shows inappropriate uses getting a piece, artificial demand getting a piece, and leakage getting a piece. And we'll have a look at that and see what those mean. So the efficiency, if you ever hear anyone talk about a compressed air system that's only 15% efficient, it's because of this. And that's what the reference is. So in Compressed Air Challenge, we do it in a pie diagram, and we talk to customers about what air actually goes to your production. And this pie diagram says it correctly. And this is what we'll be working with during the 3 days, is to see how much waste is there, how much of the air you're paying for goes to production. And this is with any plant running an air compressor to make product. In this generalization, 50% gets to production, and that's being very gracious. I do studies on plants that only 30% of the total flow goes to production. Leaks. Everybody knows what leaks are. It's a common component, and that varies by plant and maintenance. Inappropriate uses is using air inappropriately and defined as you're doing, excuse me, you're doing something with compressed air that can be done with something other than compressed air. And then we have artificial demand. And artificial demand is the extra air that moves through the pipe due to running anything at a higher than desired pressure. Anything through an unregulated end use will use more air. And we'll come back on that. So we have 3 areas that we will spend time identifying at the plant. Now here's my wow slide. I use it on every seminar I've ever done. It makes folks that aren't really familiar with compressed air start to understand why this inefficient method of doing work needs to be optimized. So here's an air motor. Anything, even an air tool or a pneumatic drill or a pneumatic impact wrench is considered an air motor. 1 horsepower of air motor, I will use 7 to 8 horsepower of electricity if I want to use compressed air. 30 CFM at 90 pounds required, 6 to 7 brake horsepower, 7 to 8 electrical power. I have a comparison here, 5 days a week, 2-shift operation using 5 cents a kilowatt hour. How much will it cost to run this air motor using electricity from this value? And here we have a number. If you're going to use compressed air to turn this shaft to develop 1 horsepower, it'll be $1,164. If you purchase an electric motor in lieu of that, that's $194. This ratio is forever. Now, we use a nickel a kilowatt hour in this reference. If it was 10 cents a kilowatt hour, the numbers would double, but the ratio of inefficiency is always there. So regardless of the amount you pay per kilowatt hour, using compressed air to do work is this ratio of inefficiency. There's a little bar chart. If you want just this little 1 horsepower worth of work, you have to be prepared to spend nearly 8 horsepower to turn an air compressor to make the air. So knowing that, you really have to think about, why am I using compressed air at my plant? What do I need it for? Can I do it with something other than compressed air? And that's what this is all about. So basically, we look at a systems approach, which means we don't look at just the compressor room. We look at the entire system and how each component interacts. We look at block diagrams, we discuss key issues, and then we discuss the assessment cost. Now, this is the 1, 2, 3, 4 step that we'll be doing during the 3 days in a couple of weeks. Here's a nice picture. It's taken from EA4, which is the ASME guidance on compressed air studies. And basically, it says here there are 2 basic ways to reduce the energy consumption of a compressed air system. Produce compressed air more efficiently and consume less compressed air. So here's my factory. It has air compressors in it. I produce compressed air. The manufacturing plant uses it. So I have 2 ways to reduce my energy. Either produce it more efficiently in here, or use less of it in here. And there's a lot of things that are components of this, but it comprises quite a bit of information. That's going to be the basis of that. I'm going to try to keep people off the noise list here.
Yeah, Frank, if you want, you can make me the host again, and I can take a track at that.
Okay, if I make you the host, will I lose my...
No, you'll still be the presenter.
How's that?
Looks like you're still the host.
Excuse me, it looks like if everyone would mute their own screen, up on the screen to the right, at the top right, there's a microphone. If you click on that, then it mutes you individually.
Oh, that was it, whoever just hit that.
Very good.
Okay. Yeah, the control panel's not working. My compressors work a lot better than the control panel. Okay. Hopefully you can still hear me and nothing wiped us out there.
You're good.
Okay, very good. So this is a great picture because, again, it talks about compressed air, making it more efficiently, and using less of it. And really, let's take a look at how we can do that. And there's only a couple of ways we can do that. So with improving how you make compressed air, it's usually compressor control. I would put in there the proper type of compressor, but not everybody's willing to give up a few $100,000 and start buying new compressors. But what they are willing is, are they controlling the compressors they own properly? So that's how we can generate the air more efficiently. And the back end, and the manufacturing end, are you running at the right pressure? And can we reduce some of the air demand? So these components here are the key. There's really 3 of them. Of course, there are a lot of subcomponents in there. Let's have a look at them. And I have this little comment here. Compressor manufacturers spend a great deal of money obtaining optimum efficiency in their product. In other words, if you're on the receiving end of being, if you're lucky enough to have a compressor vendor visit you, you'll get visited by Ingersoll Rand and Atlas Copco and Solaire and Gardner Denver and Kaiser and Quincy Northwest. There's a whole handful of them. Every one of those sales folks will tell you how their compressor is 0.5% or 1% or this percent better than the competitors. Savings is squandered in a poorly designed and managed system. So the following information can increase your productivity while saving energy. It's the information that we're going to go over. So yeah, your compressor manufacturer says, yeah, buy my compressor. I'll give you 1% more air out of it. Meanwhile, your production is using 60% wasted air, blowing out of leaks and flowing to problem areas. So the supply side isn't where it happens. 70% of the demand is where your energy savings are. Back to the compressor control. We're not asking anyone to buy new compressors. We're asking them to obviously control the compressors. Here's an example. The I-beams represent the load and unload of a compressor. Most have a 10-pound control band, and these I-beams represent 4 individual compressors. This is a cascade because typically as production's minimum requirement, theoretically as the pressure goes up, If it gets past number 3's top I-beam, number 3 will time out and shut off. If it gets up number 2, this is a typical system when you have multiple compressors to keep one base loaded or 2 base loaded, and the lower settings, they drop away. The problem is, as the demand goes away, system pressure will rise, and you could be literally running on compressor number 1, and the plant will be running at 105 to 110 pounds. There's a lot of artificial demand at that higher pressure. When the demand is higher, the pressure could be running down here at 90. So there's a lot of variance. When you're dealing with 85 to 110, that's too big of a chunk, and nobody wants to oscillate between that kind of a pressure. So this is a very difficult component when you have multiple compressors and there's no control scheme telling them where to be. Only their own control set points, and they end up fighting. The ultimate, of course, would be automation, some kind of automation and or sequencing where you take all the compressors and you tell them, well, I want you to operate at a target of 100, single set point control. And we'll give a little bit of a float, lower and upper, so the whole plant kind of floats in here regardless of the demand. And if we can hold 100 psi in this scenario with only one compressor, it shuts the other 3 off. If it needs 2 compressors to run 100 pounds, it shuts the other 2 off, and etc. So going from this, where all 4 could technically be on, I just finished a job at a bag company where they have 4 modulating air compressors. All 4 were running. Customer believed he needed all 4. My data showed only 2 are required, but all 4 ran and they shared the load. So this is pretty much the end result for optimization in a multiple compressor system. Here's a chart that looks pretty busy, but let's have a look at it here. The compressors, I believe, at Darigold and Sunnyside are, they could be modulating compressors. There are a couple of VSD, but a modulating compressor, I think I might have some annotation here. A modulating compressor follows this line here. I'm going to make it real chunky here. And it's typically, then it'll go to about 40%, and the compressor will unload to some value here. At 40% output, the compressor is still using 85% power. 85% power. So an air compressor that's rated for 1,000 CFM could be putting out 400 CFM, yet a customer is paying 80 to 90% of the power. So their part load efficiency is not good. A variable speed compressor, on the other hand, let's see, a variable speed would be, let's call it this blue line here, ideal compressor. Now, ideal compressor and or variable speed, typically the output is almost linear to the power required. Now this shows going to 0. Some variable speeds actually will unload and they'll end up sitting, you know, at a 10 or 15 or 20%, so the line might go like that. Some shut down to 0, they stop spinning, some go to 20. But if you have variable speed compressors, you're in good shape. If you have modulated compressors, you're on that red line, and you have to realize that even at 60% output, you're spending 90% power, not a good part load air compressor. So that's why we do a study of power on the system. Now, if I can get out of that. When you're dealing with pressure, there's a nice statement here. The total system may be running at a higher pressure to satisfy the needs of only one point. The high pressure application can be modified to make the lower, make the fix. So you have to study it. And during the course of the next 3 days over at Darigold, or the next 2 weeks when we get there, we will be looking for high pressure applications that maybe can be modified to run at a lower pressure. We might find applications that have a valid high pressure requirement. Now, when we say high pressure, if the plant is running at 105 or 110 and some end user says, oh, we have to run at 105 or 110 because anything below it, this piece of equipment fails, Well, that's typically a valid high pressure. And if we find it to be valid, then we find a better way to serve it. And there's a lot of things you can do. For example, next picture coming up, we have a booster. Now, if I can put a booster in, this is a very unique looking, looks like an air compressor sitting on a tank. Those are pneumatic amplifiers that take any pressure and amplify the pressure twice. So if we have a 90-pound header, I could put 180 pounds in storage. If I only have a 70-pound header, I can put 140 in storage. So we can isolate certain high-pressure requirements with these devices, then the rest of the plant can be lowered and savings can be had. The pressure profile that we create will require, and I just spoke with Oak Ridge National Labs, a fellow named Daryl Cox, and he's going to be next daying the data loggers to the plant site. And typically, we will, of course, be monitoring the power of the compressors. Now, this isn't the block diagram from Derigold, but it's similar. What I'd like to do is get a pressure transducer at the discharge of the compressors, and we may not be able to get between all the components. So one at the discharge and one after the dryer creates a pressure profile, and then we go out into the production floor and we find maybe critical end users that have problems, and we try to get a pressure transducer near them. It's not necessary to go at the piece of equipment, you know, but maybe we can get near them. So if we can find 4 or 5 or half a dozen locations, we end up building what we call a pressure profile. So we'll know the power. I'll turn that into flow. There won't be a flow meter here, but compressors, given their power, equate to a given flow. They don't really go off the mark that much. A pressure profile reveals this. Here's the operating range of the compressors. We have losses through the dryer and the filter, which could be made, in this case it shows 10 psi. We might have losses in the distribution piping. In this case, from the outlet of the dryers and the filters, which is in the compressor room, we've lost 5 pounds to some end use, so now we're down to 85. And then we have a pressure transducer at a unique end use, and that shows an additional 15 through filter, regulator lubricators, valves, hoses, and disconnects. So this is a pressure profile, and it's depicted in this point because we can actually say where is the problem. When an end user says, I have no pressure, I need to have maintenance, up the pressure, is it because the compressors are running low, or is it because this guy's losing 15 or 20 pounds from inappropriate point of use hookup, undersized piping, undersized connections? So that's key to that. All this comes out. These are the charts that we'll be looking at together in the plant. When you take your data, and we know we're going to be using a 3-second sample rate, the data will actually reveal. Now here's this is a plant. The blue line here is the discharge pressure, and you can see it's only discharging at around an average of 85. It's a compressor loading and unloading, but 10 pounds less sometimes, or 5 pounds less depending on what compressors we're loading. That's the rest of the plant. So this is pressure out of the compressors. This is pressure out of the plant. That's absolutely unacceptable to lose 10 psi out of the compressor room before it gets to the plant facilities. Now we're still on pressure. This has to do with leakage. There's no leak study here, but of course we could hear them, possibly find them if they're large enough. This has to do with pressure, though, and its association with flow. 120 pounds, an air leak through a 1/16 inch equivalent hole, a crack, a hole, 7.62 standard cubic feet per minute. If I lowered the pressure to 80, that same 1/16 inch hole would only allow a flow of 5.36 SCFM flow. Now, even though I have the word air leaks here, this could be flow. 1/16 inch equivalent diameter flow. Flow and leak doesn't make a difference. It's still air leaving the pipe. This could be a tool rather than a leak. Basically, a leak or flow consumes 42% more air at 120 than at 80. It's linear to the pressure. If the plant runs at 120 and drops the pressure 20 pounds down to 100, everything unregulated is a 20% less flow. That's the beauty of when we say to a customer, lower your system pressure. Find the lowest pressure you can run. Everyone has seen this orifice chart, and this orifice chart, and as typical, it talks about pressure and its relation to flow. The flow is all these blue numbers. And here's the individual holes, the orifices. Now, these are clean, drilled holes. Of course, the numbers here are the extreme high. If you notice, at 100 psi, at a quarter-inch hole, we'll allow 104 CFM. That's 25 horsepower. If you have a quarter-inch hole in your pipe and you run the plant at 90, that hole now is only going to allow 94. If the plant runs at 80, that hole will run at 85. This will apply to anything unregulated. Many applications can be served more efficiently by low pressure from air, fan, blower, rather than a compressed air. This has to do with the term inappropriate applications. And as we described before, anything using compressed air that can be done with something other than compressed air is considered inappropriate. Examples, cabinet cooling. That's a device that actually sends chilled air into an electrical cabinet to cool it. An example I use is if you own a computer that has, a desktop computer has a little fan on the back. Well, if you wanted to cool that with a compressed air generated cabinet cooler, it would take about 25 CFM. You would need a 5 horsepower compressor running next to your computer to cool it. Be a nice perk when you purchased one, but certainly inefficient. Liquid agitation, stirring, making bubbles, vacuum generation, open blowing, air motors, atomizing. Every one of these can be done with something other than compressed air. Again, this poor practices, 5 to 10%. I just finished a bag company, as I mentioned. One of the things they do, besides extra leakage and their compressors running inappropriately, they have ink, 50 ink agitators. Every press that makes paper bags has ink to make the labels, and they use little air motors to stir the ink and pump it into the press. Each motor is 25 SCFM. They have 50. You do the math. There's over 1,000 CFM. That's over 200 horsepower just to mix the ink. Quick shot online to the same company, and lo and behold, they make electric conversions for all those ink tanks. It's all water-based ink. Years ago it wasn't. Today it is. And each one's 1/8 of a horsepower, fractional horsepower. So there's about a 700 horsepower, actually almost 800 savings. It's just an amazing what you can do when you say, what am I using compressed air for? What can I do with other than compressed air? So one of the things that we tasked the folks at Sunnyside with was give me a block diagram, and we're still working on it, but we got compressor room number 1 that has 100 horsepower, 50 horsepower, and a 50 horsepower. Looks like it's connected, goes through a filter, through a dryer, into a 2,000-gallon tank. That's a separate compressor room. We have a large picture here, which is pretty hard to see. I think you can actually see the compressor room location and the 3 rectangles. That's the location. We'll be observing that on site. This looks more intense than it really is, I'm sure. Compressor room number 2 has a 125 horsepower compressor, a 100 horsepower compressor. Some are modulated inlet, some are variable speed. Common 4-inch header, filter, dryer, 400-gallon receiver. For example, when we talk about hooking up a pressure transducer, just to give you an example, I probably would put a pressure transducer here. That would be the discharge pressure. And then maybe we put a pressure transducer in the receiver. And the difference between the two would be the loss through the filter and the dryer. And that's good to know because we might have 90 pounds out here, but the compressors might be looking at 105. I'm just making this up, but it's an example. We need to know that because without an automation system, compressors base their decision on this pressure because compressors don't see this pressure. So unless these compressors had automation where they were looking at this tank they're not going to be looking at anything but their discharge. What a mess. So we can do that. That's what we always find. And a lot of customers say, nope, our compressors are doing just great. Unfortunately, they never are. This compressor number 2, right here in this picture, there we have it, 2 compressors. And then compressor room number 3, I don't have a diagram for other than this. This is the newest of the compressor rooms. It may or may not be operational. One's a variable speed and one's a fixed speed. Technically, compressor room number 3 could run the entire plant. So during in 2 weeks when we do the study there, these may or may not be operational. We don't know. We'll find out. If they are, that's great. They run into a common header, dryer, bigger tank, 3,800-gallon tank on the dry side, and then filters. So there's the compressor room block diagrams. And then we have one cheese packaging area. This is out in the demand. If, for example, if cheese packaging was a critical pressure area, then I would make sure that we put a pressure transducer next to maybe a case packer or a palletizer. Depending how close these are together, we might say, let's just put one in the header. And it could be even a drop line or a gauge. So we need to create the profile and see how that air is moving through the pipe. Is the pipe capable of handling the flow? Pressure drops are created by restrictions in the pipe or excessive flow in the pipe, which is technically a restriction. If you try to push too much air through a pipe, the pipe itself is indeed the restriction. Pre-assessment information was sent out. Customer did some checkoffs. I mean, you can see that there's a lot of things to check off here. Improved reliability, production interruptions occur, poor quality affected by compressors, compressors don't achieve full capacity, we need to expand. What the one item that was checked off at this Sunnyside plant was we need to reduce air demand and lower energy costs of operating our compressed air system. So that kind of becomes the scope of those few days. Now, in the process of let's find out how Sunnyside can reduce air demand and how they can lower their energy, a lot of these other things fall into play also. This is a checklist that was, well, nothing was checked off, but potentially inappropriate application. So during the, we will have groups. I need to have groups because in the 2.5 days that we're there, it's just way too much information just for me alone to investigate. The beauty of it is that we have everybody to go off in little groups, and after we go over like the first day and I explain what we're looking for, you know, everybody goes off and does their thing and comes back and we report out once or twice or 3 times in the daytime and see what we've discovered. Look for open blowing, sparging, which remember that's bubbling, creating air bubbles using 100 pounds of air, aspirating, atomizing, padding. Padding is pushing liquids with air. Dilute phase transport, dense phase transport, using air to transport material. Vacuum generation, personal cooling, the workers blowing air on themselves, open hand blowguns, cabinet cooling, venturis by vacuum, diaphragm pumps, timer drains, air motors. So all of this stuff becomes what we look for. Let's take a look at some of the tools that we'll be using. And AIRMaster, and everyone can download these free, AIRMaster and log tool from the DOE website. The AIRMaster tool, as old as it is still quite functional. I use it on every job. Measure, calculate baseline, 24-hour metered airflow or power. We can put the actual electrical utility energy schedule in there. We can do what-if scenarios, simulate compressed air system operation. We can do anything we want. The best part of this is the what-if scenarios. And then we estimate savings. So once we put in the profile, we actually say, if we did this, what would the savings be? If we lowered the pressure, if we shut off this air compressor, if we change this piece of equipment and stopped using this. Anything you do with AIRMaster software ends up with a new baseline and a reduction in energy, and it's very valid because we made sure it's valid. So you end up filling out this software tool. We already have it filled out for the Darigold at Sunnyside. This is an example of a 3-compressor system. Every hour is labeled, the kilowatts or the amps, whatever is recorded. We can record kilowatts, we can record volt amps. We'll be recording amps, and I'll be applying the right voltage to it. And the calculator already knows the power factor given the motor size, so it'll be very accurate. It's not just going to be amps times volts. It's going to be amps times volts times power factor times 1.732, and we'll get a true kilowatt from that information. Beautiful graphics come up showing either the flow, the power, or the percent capacity of every compressor that's running. We can look at EEMs, energy efficiency measures, reduce leaks, improve end-use efficiency, reduce system pressure, changing the controls on the compressor, put a sequencer in, reduce runtime, add more receiver capacity. I can do any one of these 7 items in the checklists within AIRMaster, and out comes a brand new savings number. And if you think there'll be a cost associated with it, so will there be a return on investment column. Really, really trick software, works wonderful. But in order to do it right, we need another piece of software that's called LogTool. And LogTool actually allows us to look at the data. So we can do trend plots on y-axes, really cool stuff. Let me get to the actual thing. It's another one of these boring faces where you put data in, you download it. We'll be using Hobo data loggers. The click here, this is not live so I can't show you, but logger file type, there's like 9 different data loggers, so you can put in data from anyone. It even has a generic CSV file format you can use. Once you import the data, everything you have, kilowatts or pressure or amps, whatever, you can put and trend on 2 different axes. And it's really cool because then you can just click what you want to look at on axis 1 or axis 2, Y1 or Y2, and it pops right up. Really, really nice stuff. It allows us to look at day types. Day types in AIRMaster mean, does the system run the same every day? And no system does that. Here's one system, power is being monitored, and it shows that on the weekends, this customer is running 200 kilowatts. But during the work week, they're between 300 and 400 kilowatts. Well, what happens during the customer's weekend? Why are they using 200 kilowatts? Well, why? In this particular job, because maintenance is there, and they turn on one air compressor worth 200 kilowatts. Maintenance has a couple of tools, so this is 200 kilowatts of air that's leakage. So this is an instant gross leakage test. And we pick the day types, we highlight it, we output the data into the spreadsheets, and from this spreadsheet, we go right into AIRMaster and we have everything done for us. Really cool. You can trend plot it with this graph. Now, it looks kind of busy because we have 1, 2, 3, 4, we have all these days here, but you can strictly click in on a rectangle and zoom in. You can zoom in as close as you want, and you can see the timestamp changes. And once you zoom in, if I did 3-second interval, I would exactly know what every 3 seconds was going on. It also lets you do scatter plots. Scatter plots is another thing we'll look at, where here's a compressor that has pressure scaled on the x-axis. It has kilowatts scaled on the y1 axis. So I know when this compressor loads, it loaded at 117. It was pulling 90 kilowatts. It went all the way up to about, that's probably about 95 kilowatts at 124. Then it unloaded, blew down, and the unload power is about 25. Lots of good information on these scatter plots. And again, you produce these charts. LogTool is the companion needed for AIRMaster, and we'll be going over both of these. Here's a company that you can see uses 10 kilowatts, and then their shift starts at about 8 or 9 o'clock. It goes all the way up to 40 kilowatts, and their shift ends at the hour is 18 or 1900. So anything is possible with the tools. And then again, the spreadsheets that they create, it's overwhelming now looking at it slide by slide, but it's super easy. And within an hour's time, in real time, while we're doing this on day 1, I can show you exactly how to use it. And most of you might even know how to use it. So let's take a look at our actual on-site. So the system engineering focuses, defines the stakeholders' needs, sunny side, from energy input to the compressors to the work performed in the production area. And that's what we're going to analyze. Point of use as it supports critical plant production. Basically, we're going to learn how does compressed air support production at this plant? Why are they using it? What are they using it for? What does it do? We'll correct existing poor performance applications if we find them, and those that upset system operation. A big air user, a monster bag house, a big dust collector. Those are things that upset system operation. Diaphragm pumps, all these things. Eliminate wasteful practices, leaks, artificial demand, remember that's pressure, inappropriate use. Create and maintain energy balance between supply and demand. That has to do with, are the compressors controlled? Are they putting the right amount of air into the pipe? Or are they putting more than they need? If they're putting more than they need, air pressure is rising. If they're putting less than they need, air pressure is falling. The goal is to have the compressors put just what we need into the pipe so the pressure is stable. And we can do that. We can optimize compressed air energy storage. Air compressor control, you'll learn about storage. Storage is critical to a system's stability. So the following is a typical 3-day assessment agenda. Safety briefings, tour of the plant, team agrees on potential energy opportunities, investigates, begins data collection, and that's day 1. Day 2, data collection continues. Software assessment tool is applied to quantify potential opportunities. Every day when we're there, we'll be able to pull data and have a look at it using the software tools. The lead person at your plant, qualified expert, discuss and agree on the opportunities identified. By the end of day 2, we'll know exactly what this plant can move forward on, what's worth implementation. Some implementation just cannot be done. Some of it is absurd. Some of it is like a no-brainer, the low-hanging fruit kind of thing. Wrap up the software tool analysis, focus on answering questions, and by midday of day 3, we're pretty much done. So we actually have the agenda, 8 to 8:30, arrive at the plant. Everyone has this or should have it. Compressed air energy management training. So this is the actual agenda that looks like we're going from 8 to about 4:30, and it's everything we just talked about, and discussions and tours and demonstrations, just so we can get teams together and help identify. Wednesday, which would be day number 2, starting at 8 o'clock and again 4:30, data collection, discussion, the software tool is utilized, more data collection if we need it, more discussion. And on day 3, we start in the morning, questions and answers from the previous. We have to finish because I personally have to be out of the system at 12:30 to catch a flight back in Seattle. But then the bulk of the equipment and the data logging would have already been done and downloaded at the end of day 2. So it's a pretty rapid pace that we're going to hold. You know, and if these lunches and coffee breaks prove that they're not going to work, we might even do working lunch breaks or working coffee breaks. You know, while we discuss the data, we can all be having coffee and stuff like that. So it works pretty well. This system is going to be good. We're about, about an hour, a little over an hour into this now. Paul, who's the Technical Assistance Manager, or the TAM, and myself. I'm not sure if Vestal is going to be on site. I'm not sure if Vestal, will you be on site during this at all?
I will not be, no.
Okay, all right. So I think, I hope I didn't go too fast, but I wanted to leave it for questions. Any more, it tends to get boring and obnoxious because it's a lot of information. And so we'll just leave it open right now. Let's go for questions.
All right. This is Vestal. I've tried to unmute everyone, but if you're not speaking, I do request that you put yourself back on mute during that time. But I did not receive any written questions for Frank during this presentation. Frank, I thought it was a very, very informative presentation. Did a nice job. I apologize for the glitch in getting things muted there at the beginning. But
Oh, no,
yeah,
I can
open
put
it up.
this in a PDF if anybody wants it, by the way.
Yeah, that would be great, Frank, if you don't mind.
Is that Paul?
Okay.
This is Paul, yeah.
Oh, great. All right. Well, I'll let you lead then, since you're still on the line.
So, yeah, thank you, Vestal. So, this is a great time for any questions for Frank. He did go over a lot of really good information. But now's your chance to ask more detailed questions.
Hey, Frank, this is Todd from Darigold in Linden. Can you give me the website that I can download the AIRMaster and Log Tool software that I might have it up? I might be able to put it on
I can provide that, Todd.
Get with me.
Yeah, Tom, someone answered you. Who can provide that to Tom, or can that be provided to everybody? I mean, I personally go to the compressedairchallenge.org, compressedairchallenge.org, and you'll see the link for the training software, which will probably link you to the DOE, but that's the one I remember, compressedairchallenge.org.
I'll forward that out to everybody at Daily Gold.
Thank you.
Thanks, Uli. Any other questions? Frank, that means you did a remarkable job. You answered everybody's questions before they asked them.
No, that's my goal. My goal is always to do that. So.
Well, I guess if we don't have any questions, I'll give it another minute, but then we'll call it quits for today and get ready for meeting at Sunnyside.
Okay, awesome. Thank you very much. Is there anybody from Daily Gold that we did not get on the roll call? Awesome. I think we got everybody.
Very good.
So it sounds like everybody's starting to drop off, so I think it's time we'll just end the webinar, and thank you for attending. Thanks, Frank, for the great information, and we'll look forward to seeing everybody in a couple weeks at Sunnyside.
Very good. Take care.
Bye-bye.
Thanks, everybody.
Bye-bye.